Yeah, just right next to the heart. Go to the next to the heart.
I think I got
Yeah,
it.
no, you got it.
Oh, you got it. When you good.
Yeah, and so SpaceX posted a video of like all of their landing rockets crashing. So there's like dozens and dozens that have crashed. And then in about 2 years ago, they were finally able to land two simultaneously within seconds of each other, which is crazy. So now these can be reused, and they reuse them all the time now. So it's almost second nature to re-land your rockets, which is all possible because of the embedded systems running in here. Another great application of this is something super basic, right? So next time you're in your car, any cruise control or adaptive cruise control that's happening is all a result of the embedded systems inside. So for example, your microcontrollers internal to your car are sensing things like speed, acceleration, how much energy you have left in your fuel tank, and are constantly adapting the amount of throttle left to keep like a constant speed, right? So your microcontroller is taking in all these sensors and all the data from them, so sensors, and then outputting control to the throttle to make sure that you can keep your constant speed. And with adaptive cruise control, they add another layer to that where they're also measuring the distance to the next car, right? And so all the embedded systems running inside this guy and all the code that's written in there is responsible for all of this interaction, for keeping the driver safe, keeping your constant speed. And this gets even harder when you add self-driving cars into the mix. So all of that happens within an embedded system. And that's what we get to do in Team Phantom and what we're learning about today, which is great. So there are a bunch of different types of embedded systems and processors, integrated circuits, and all those things. At Team Phantom, we work on microcontrollers, so that's these guys here. You can often see the acronym MCU for microcontroller unit. Some people also like to kind of put like a micro C symbol if you're kind of lazy. That also works. So the way a microcontroller works, essentially it's a processor inside, so it has a little mini CPU kind of deal. Wish I could write a C, okay. And a bunch of other little cool building blocks. So all these other little things are completely integrated into this one big chip, which is great. Back in the old days, for the power of CPU that we have in here, you didn't have any of this other additional function inside of your microcontroller. So what all these little building blocks do is they give you the opportunity to interface with analog signals, send out pulse waves, communicate with different chips via different protocols. And a lot of that is built in, which is one of the great advantages of a microcontroller, because it's so low cost, but it has all of these things built in, so you don't need a huge system around it, right? So you have a lot of integrated stuff. And usually we call these kind of building blocks peripherals. And you can have a whole bunch of different ones. And based on the microcontroller you pick or use, you'll have a different set available to you. Now this middle guy here is probably familiar in terms of the logo, which everyone agrees to hate, but it's not super familiar in terms of how much work we do on these things. This is known as an SoC, or a system on chip. So SoC. This is one of the more popular inventions in the processor side in the past few decades. And basically what it does is it's almost like a microcontroller in the sense that you have so much stuff integrated, but it's kind of like an upgraded version, right? This is what powers things like the iPhone, tablets, laptops. Basically, most portable smart devices are powered by SoCs these days. Solid state drives, things like video conferencing equipment, all of that is powered by an SoC, so a system on a chip. And this has a much more powerful processor than a microcontroller. And it's similar in the sense that you also have a bunch of building blocks added in, but these building blocks are more sophisticated. So it has usually all of the same kind of basic ones, but you start adding really important and useful things that you need for a phone, for example. So you want to display a bunch of stuff. So there's a built-in GPU right inside that chip. There's a built-in wireless controller, so you can start interfacing with antennas and data services. Some of them have built-in engines to run specific types of math, built-in power units, built-in battery management. And so like it's a really amazing invention that they came up with to combine a processor with all these other little things. And it's great because it's low power, right? That's one of the huge advantages and why people like it in these portable applications. And for these, like another big difference between a microcontroller and an SoC, for example, is that operating system. So these things are capable of running something like an iOS, right? iOS, Android, Linux are all very popular on an SoC. Whereas a microcontroller is a lot more streamlined. It doesn't have this huge operating system that runs around it where you can develop software on. It's super streamlined and really quick. So people love microcontrollers if you have a really specific task, a really specific application that you need to interact with the real world. So cars, like in like Team Phantom's car, Tesla's, most cars use a lot of microcontrollers in there to do all of this interaction with different sensors in the car, a lot of different motors. So things like seat motors, heating and cooling, all your window motors, automatic doors opening, and then again, all that cruise control type of things as well. Where you move to SoCs is when you start to add more intelligence and operating systems, when you have cars that are doing things like self-driving. There you have a whole other set of software that you need to develop. So things like machine learning models, neural networks that train on these are a lot more sophisticated. Now on the far right, you have your general CPU, right? So this is a Intel Core i7, should be pretty familiar. So this is a CPU. Some people also call them MPUs, microprocessor unit. Central processor unit and microprocessor unit are basically exchangeable in this case. And the idea is that it's the most powerful of these three, right? This has most power. And this is what your computer is going to run on, right? This is what's in my laptop right now, and what most people prefer in terms of having that computing power available. Downsides to it compared to an SoC don't have as much integration, right? So you can see that this chip is going to be one chip on a huge circuit board that has a bunch of other ICs on there, so integrated circuits for things like external RAM, external memory. You have an external GPU, as you know, that you're going to plug into your PC, and so many other things that aren't completely packaged like they are in an SoC. But the benefit is that you can add as much as you want, right? And if something breaks externally, you can replace it easily. You have the capability to upgrade, and you don't really need that low power that you have in an SoC, because in those SoCs, they're meant for portable things, right? Portable phones and cell phones and tablets. For your CPUs and MPUs, a lot of them are just held in desktop computers and laptops where you don't need to conserve as much power as possible as like in a phone. So that's a quick breakdown. In Team Phantom, anyone want to guess what we use? This is our guy. We don't really need to run huge operating systems. We want to do very specific tasks very quickly without all that huge overhead. And so sometimes we'll add a very light operating system on top of our microcontroller, but most of the times it's not super necessary. So here's an example of one of the vehicle controllers inside a Model 3. So this is the front controller. And there's actually 3 inside of the Model 3 that all look kind of similar. So you have the front one here, and then you actually have a left controller and a right controller that are a little smaller, but kind of on the same order of scale, that run all of the body electronics in the car. And so you can see right here is our favorite microcontroller, right? So this is not an SoC, this is not a processor, it's a microcontroller itself that's running inside the Tesla, doing a lot of the different functions to control all of the body work. So you can see these are actually motor controllers right here. It's tough to visualize, but there are 6 transistors and a gate driver chip. And these act as motor controllers to spin a lot of the motors inside the car. So whenever you turn on your AC and you have a whole bunch of air blowing out at you, that's controlled by this microcontroller talking to a little motor controller on board. And any other sensors that control that airflow, control that temperature are read in by the microcontroller. And so it takes in a lot of different sensor inputs. You can see every single one of these little squares. Those are all switches and transistors switching on different outputs of the car and taking in different sensors. And so there's a lot of work that goes into writing these embedded systems for vehicles, especially for production vehicles, but even for us as well. There's a lot of work that goes into interfacing with all the sensors and actuators inside the car. The battery management system, which is something that manages an electric vehicle's battery, is very similar as well. So this is the Model 3. You can see here's your processor. Here's where all of the BMS slaves would connect. And this is the BMS master inside the Model 3. So BMS stands for Battery Management System. It's basically placed there in order to control the high voltage battery within an electric vehicle. So making sure all the voltages are in place, making sure that nothing gets damaged, there's no fires, and that we have the proper safety measures in place in case something goes wrong. So this BMS master, very much like ours, would talk to a bunch of slaves. So there's actually 4 of these slaves inside the Model 3, and 4 inside Team Phantom's car as well. Big coincidence. And what these slaves do is they actually specifically measure all the battery voltages and currents and temperatures, right? So battery state. So with all these slaves measuring the battery state, the master makes a decision on what to do. This is an embedded system that is very critical to any EV. If something is going wrong with the battery, then you need to make sure you take the proper precautions to keep everyone safe. So in our car, we have a great team working on our BMS, and they're doing a lot of work on the safety, measuring temperatures, measuring voltages, to make sure that everyone's kept safe. Without an embedded system, we would just have a car and a big block of batteries that does nothing. So it's critical that these systems are in place for us to work. If you want to go a little more sophisticated, this is also the Model 3. This is no longer a microcontroller. I don't know if you can tell, but so this is Tesla's full self-driving computer, and they call it an FSD, right? And this is what allows them to enable autopilot. So these are fully blown SoCs. So this guy. So these are both SoCs. This is a fully redundant architecture. And what that means is that we have 2 SoCs or 2 brains or 2 processors running the exact same commands and making sure that in case one fails, the other one can take over and keep the car running as needed. So this is a great technique, and it's often used in the aerospace industry as well. If you launch a satellite or a rocket, what you'll do is, because of the dangers of radiation, a lot of the instructions can get messed up or things go wrong due to the harsh environments. And so what they do a lot of time is they have a redundant architecture, often with 3 or 5 different processors all running the exact same commands. And what this does is that if some of the processors disagree, then all of them vote on the best way to go, right? So if this guy says, I think we should do A, I think we should do A, I think we should do B, but these guys also say A, then you're going to go with action A, whatever that is. And so Tesla implemented the same thing in their self-driving car, just in case one of them breaks, right? So you have that redundancy. If one of them breaks, then the other can take over. Same thing here. You have up to 4 can break almost. And you can still keep going with what you need. In Team Phantom, we actually kind of do something like this. It's not exactly the same, and we definitely didn't come up with it at all. It's just a byproduct of the microcontroller we're using, which is great. Yeah, so in this SoC, you can see that there's so many chips around it, right? It's not completely integrated. The SoC has a lot of stuff inside it, but it still relies on a lot of external memory to be able to run those huge operating systems. I believe these run Linux. You can see each one of these chips here. This is all external RAM. Each one of the SoCs has 4 outside of it, and those are needed to run Linux and have a really fast operating system. And these chips are optimized for machine learning models. And so the future of AI and machine learning, right now it's based mostly in the cloud, right? So you have your embedded system interfacing with all the signals you need. You send that to the cloud runs the machine learning model, gets the data and sends it back to your embedded system, and then you do the output. People are now optimizing their chips and their processors to be specifically optimized for machine learning models. So all of the dot products and linear algebra that you need for a neural network is optimized to be really fast in these new chips. And that's why Tesla decided to start making their own. So before they used to use NVIDIA, because NVIDIA does a lot of work for self-driving and different architectures, but eventually they started making their own because they wanted to accelerate the move towards specific silicon within those chips for machine learning. And so there's a lot of interesting things that are happening within the embedded space and within the processor space, even from companies who have no business making processors. Someone tell you on that. But they like to go crazy and kind of make everything themselves, which is pushing the industry in terms of self-driving, which is great. So Team Phantom, until you guys start a self-driving car, we're doing this for now. And some of this may change, especially this bit, but we'll talk about it for now as it is. And so each of these kind of purple squares, so this is our full car, right? So this is what our car looks like. It's very square shaped. Each of these purple guys is a microcontroller, right? So an MCU. We don't need to run Linux or Android or Windows operating system in any of these because we don't need that power. We don't need to develop new software on it, like writing websites and all those things. And so for now, these microcontrollers, which are very specific, very low overhead, not a lot of bloatware on top of them, are perfect for our application. And so the VCU and the BMS Master both use a microcontroller called the TMS570. That's just a chip from TI. We can talk a little bit more about that on some other day. And Mahmoud should be giving some tutorials specifically on that over YouTube, so you can check those out as well. For the VCU, we're measuring a whole bunch of stuff, right? There's all this stuff here. All this stuff that it's measuring. These are all inputs, right? And they come in over different means via either an analog signal or a digital signal or some sort of communication protocol that we'll break down a little bit later, maybe in a different lesson. But it also sends an output, right? So what the VCU does is it controls the torque request for the motor. So what it's doing, this inverter is just a motor controller, right? This is controlling the motor that's moving the car. And so based on all of these safety sensors and all of the things that are happening in the car, the VCU will decide if it's safe or not to actually move. right? And it'll determine based on the foot pedal that the driver is pressing, based on the state of any of the high voltage buses or isolation, whether we can actually request torque from the motor. And so based on all these checks that we write, it's going to determine the safety of the driver, right? And if we don't write the right firmware, if we make mistakes or do something wrong, then we could seriously negatively impact the lifetime of our driver. All it takes is some code written wrong for the VCU to go nuts and accidentally request max torque when everything's broken, right? And so it's up to us to be very careful with all of our firmware. BMS Master talks to all those slaves, as we mentioned before. So it talks to it over serial communication protocol, which we'll talk about another day. And each of these slaves chats with the battery, right? So it's measuring the high voltage battery within the car. Now what's nice is that the BMS Master doesn't need to talk to every single one of these, right? We're able to just talk to the top slave or the bottom slave, and that one can send the signal down the line, which is really great. And this slave can send its signals up the line all the way to the BMS Master as well. And we have some great developers on the team who are working on this right now and getting all that data from the slaves, making sure it's all within the right bounds, and making sure that we can be safe. BMS Master also talks to the thermistors, which is cell temperature monitoring, and then these interface with the charging shutdown circuit, which can shut down the car via hardware, and also the charger when we need to. The dashboard is a great example of a monitoring display. So it takes data from the CAN bus, which is a communication we'll talk about some other day, and all of the other microcontrollers and systems in the vehicle, and it displays them to the driver. So things like speed, battery life, any faults that are going on. And this may be updated to a different type of processor. So it may go to something like, or it's people are working on right now going to like a Raspberry Pi, which runs Linux. And it's mostly to be able to display like a GUI type thing. So it's a little easier for the driver to see what's going on and help us debug. But there are definitely different options depending on what you're hoping to do. This is kind of an overview of what's going on inside the car. Do you guys have any questions so far? Cool. So we'll keep going. Bug me anytime you have a question. We want this to be more of a discussion or like a back and forth so we can chat. And if you have anything that I missed or you want to bring up, especially you embedded people, feel free to butt in and interrupt me right away.
There's a question in the chat.
Yeah, so most of this is written in C. So I can put it like here. Oh, most of it's written in C. That's mostly because it's the closest language to assembly, which is what the microcontrollers need. And so the compiler on your computer where you write C, so like on a computer I'll have a different software where I'm going to type in all the code. Once I load it onto the microcontroller, that's translated down into assembly, and it goes onto the processor. There are some ways to write higher level code, so things like C++ and even Python, where someone else has written a library to translate it down into C for you. But then you lose a lot of control over what you're writing and all of the variables and the memory you're using. And so we like using C because you get enough control over what you want, but you're not so strapped down by writing something like assembly, which is a lot more work, that it's just takes forever to do anything. So C is a nice sort of in-between. Cool. Now that we have sort of the intro of what embedded is out of the way, we can start talking about some of the concepts. So can somebody tell me the difference between digital and analog?
Digital, square, analog, curvy.
Curvy. I like it. Okay, keep going. What else? Anyone?
Digital 0, 1. Analog is more of a sweep ranged. 0, 2, whatever your upper limit.
Got it. I wish I could click my pen.
I don't get it. We're clicking it.
I know. Damn it, embedded.
Wait, you click? Oh, I see. It doesn't actually click.
What if I do this? Okay, no more writing. So I heard, what did I hear?
Rude.
I heard square, right, John?
Yup.
Yeah.
Square and curvy. I heard 0, 1. And then a sweep. What else?
Can you make that bigger?
Yeah.
Then you can just write in the same one.
Okay.
Thanks.
Okay. What else we got? 0, 1. Can digital be more than 0, 1?
I would say that digital is set to a voltage, so you should know what to expect, basically.
Okay, good to know. These are all right, for sure. I think the tricky part with digital is that, I think the defining characteristic is that it's a finite set of values, right? Finite set of values. And analog is almost an infinite set. So digital can be a 2, right? It doesn't have to be 0 or 1. You can have something that looks like this. Be digital, right? And we kind of intuitively understand the analog is sort of like, you picture it as like more smooth, right? Like a kind of curvy thing, like these guys said very intelligently. And so infinity, eh? So if we have like some limits here, analog has almost an infinite number of tiny little steps in the whole range, right? You could keep zooming in all the way and keep finding more and more little steps. Whereas a digital signal, you very quickly see that there's a very finite set of steps you could be in, right? And you'll see this all the time going from the analog domain, right, to the digital domain, and the digital domain to the analog. And it's funny because there's a converter for each of these. There's a whole system, right? A converter that does this conversion to switch between these worlds. Because our microcontroller is digital. It loves digital world. It has no idea what analog means, right? But we sort of trick it and we find these ways to convert between the two worlds. And what you can do is measure an analog signal and sample it into a digital form, right? And you can turn a digital waveform into analog. But this way is not super perfect. You can never get back to infinity, right? If you start with some finite set of values, you can only get to a finer or bigger finite set of values. You can't really go back to make it perfect. And so
I have a question.
we should talk about this. Yeah.
Can you normally have a negative digital signal, or can it only be positive?
We have different ways of representing it. You can definitely represent it or negative, but the easiest way is usually just to keep it positive for sure. So like if you wanted to keep it simple, we could just do this, right? Oh, that's close. You get what I mean. But yeah, there's definitely ways to represent it in terms of signed versus unsigned and two's complement and all that stuff. But it's easiest to just keep it positive. Cool. So digital signals. Binary is probably the most fundamental building block. So this just means two options, right? Binary is just one of two, so it can be a 0 or a 1. And exactly like Jared said, this is how computers work in the real world. They care about a 0 or a 1, and they usually don't have access to those infinite sets of values the way analog signals do. And so to be able to convert and to actually interface with the real world doesn't really know what a 1 or a 0 means, right? Only our computer, our microcontroller knows what that is, right? So it's essential to understand something called the logic level. So a microcontroller will have some sort of logic level, right? And it's going to be different depending on the microcontroller you use. For us, that's usually 3.3 volts. And what that means is that if your logic level is 3.3 volts, that's the level at which you read a logic 1, right? So if my microcontroller is seeing 3.3 volts on one of its pins, then it interprets that as a 1, right? So if I have my graph, it looks something like this. And this is 3.3 volts. This is 0 volts. The microcontroller is going to read this voltage and interpret it as a 1. Read this voltage, interpret it as a 0. And based on the logic level you have, this will be different, right? For an Arduino Uno, for example, which is a very popular microcontroller, that logic level is 5 volts. So Arduino Uno, 5 volts, right? So this wouldn't mean anything to it. An Arduino would just read this as 0, 0, 0, 0, 0, right? Until it saw a 5-volt signal. And the Arduino would read this as a 1 and a 0. So this logic level is basically the way that the microcontroller interprets the real world, right? And it doesn't have to be absolutely perfect. Usually you have a little window to play with. And so if your Arduino Uno has a logic level of 5 volts, then let's say that my signal only hit maybe like 4.7, right? The Arduino is reasonable, right? It's not a bad guy. It's gonna be like, that's close enough. So it's gonna give you a 1, and you'll be happy. This range is usually called VIH, the voltage input high level. So it's a little bit of tolerance that the microcontroller gives you, so that you don't have to be absolutely perfect. You can be within a little range, and as long as you're above this voltage input high range, then it'll consider that a logic 1. Even though the logic level is 5 volts, you can be close enough, right? Same thing with your logic 0, right? You have a little threshold here, so you don't have to be absolutely 0 volts. You could be maybe 0.2 volts, right? And that's called the voltage input low. So same idea. It gives you that little tolerance so that you're not freaking out. You don't have to have absolutely perfect electronics, but you do have to be close, right? So it knows what you're talking about. So you can represent a lot of numbers with our zeros and ones binary. Does anyone know how to do that? So if I had like a, let's say the number 10. So this is in, sometimes I put brackets around it to be very clear, in decimal. So the decimal base is just how numbers work normally, like 24 or 35. we have the decimal base adopted as our current way of communicating, right? So the 10 has 2 placeholders, right? Our number 10 here. And each placeholder can take up to from 0 to 9 different values, right? So that's 10 different values in each one. When you're in binary base, each placeholder can only take, you guessed it, 2 levels, 0 or 1, right? 0 or 1. Right? So if I put a number in here, so like I put, let's pick a better number. I don't like 10 anymore. Let's do something like 7. Maybe 7. Let's do 13. Right. What this really means, what's happening here, is that we're taking the first one. Let's start with the 3. We have the 3 times 10 to the 0 plus the 1 times 10 to the 1, right? If I do the math, that's 10 plus 3 is 13, right? So that's how you represent a decimal number. Binary is the same way, right? We had 10 different options here in the 0th place. We have 10 different options here in the 1th place. It's the same thing, but we only have 2 options in each one, right? So each one of these placeholders gets represented by one of these. The same way this would be 10 to the 0. This would be 10 to the 1. If we had more, it'd be the hundreds place, right? And then the thousands place, and keep going on forever. So if I had a number, something like 101, right, in my binary, what that would mean is that I'd have 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0, right? And what's that? So that's something like 4 plus 0 plus 3 to 0 is 1, 1, which should be 5. Is that right? Did I make a mistake? I think that's good. Right, so this is just a different representation. This is a different representation of the same number, right? These mean the same thing, 1, 0, 1, and 5. It's just that we can represent it in binary or back in our easy, convenient that we like decimal, right? So how would you guys create the number 13 in decimal? Send it to me in the chat.
You mean in binary or?
Yeah, I realized I said in decimal. Okay, that was easy. Good job. In binary, sorry. Thank you. John, do you want to walk us through how you'd convert that? John, please.
Sorry, I was eating.
How would we do this?
Trying to remember how I do this.
Google decimal to binary converter.
Oh, please. No. So
2 to the power.
so this was 2 to the 0, right? 2 to the 1. And maybe we need more placeholders. I don't know. Maybe go to 2 to the 4. So in each spot we have the option to put a 1 or a 0, right, John?
Mm-hmm.
So you tell me what's
2 to the
what
4
should-
would not be good because that's
2 to the
16.
4. Why is that? 16?
16's too big, right?
That's too big, yeah. So we don't want to go there. Okay, that's good. I like that. What else could we do
And
here?
next is 8, so you put a 1 there.
8. Okay.
The next is 4, so 8 plus 4 is 12. So you
Okay.
put a 1 there. And the
Seems
next
legit.
one is 2 to the 1, so that's 2. But 8 plus 4 plus 2 is 14, which is too large. So you put a 0 there. And then you put a 1 on the last one. It's just
Nice.
a 1.
I like it. Perfect. Easy, right?
Yeah.
So, yeah, I like how you started from the left. You can kind of see what your biggest one is. So this would be too big, so we don't want a 1 there. And then a good trick is if you ever notice it's odd, you know that there has to be a 1 in the 1's place, right? Because everything else is a power of 2, right? So it's going to be divisible by 2. So if you ever have an odd number, you're going to have a 1 down in that 1's place. And that's cool. What's important to remember is that these mean the same thing. These are the same number, right? It's just how you're representing them. And we're going to see that often in embedded, you can represent the same number in multiple ways, right? So you could write that your variable equals 13, or you could write that it equals a binary number, and it'd be the same value, it'd be the same essence of what it is, just represented in a different way. So we're going to use this a lot, converting between binary and decimal later, especially when we're doing things like communication protocols and reading different sensors. It's going to be useful to read things in binary. So now that we know how a computer works, 1s and 0s, and we know what the logic level means, so let's go back to our 3.3 volt logic level. Sometimes you can write 3v3 instead of 3.3 volts. And that's common in terms of history because on old schematics, people would write 3.3. You can see this dot really gets lost, right? And sometimes you think of it as a 33 volt or it was misprinted and you can't tell. So 3v3, instead of saying 1.2 volts, people say 1v2. 5 volts is easy. But that's just a common notation that people like to use and that probably to use from now on. So we know that 0 and 1 with a 3.3 volt logic level would become 0 and 3.3 volts, right? 0 volts. So the first way, and probably the most fundamental way that the microcontroller can interact with the real world is through what is called a general purpose input and output. So general purpose input output. And this is a digital peripheral or a digital building block inside your microcontroller. And basically what it does is it allows you to send out digital signals. So from your microcontroller, this is our guy. I can now send out a digital signal if I want. I could send a 0 or a 3v3, which is a 0 or a 1, right? Or I could read in a 0 or a 3v3, 0 or a 1. And you have to be careful because based on the logic level of your microcontroller, it may not be compatible with other logic levels. So if I have a 3.3 volt microcontroller, which we do, all the Team Phantom ones are 3.3, so be careful. If I'm trying to read a 5 volt signal, that may damage the pin, and it may kill your microcontroller. Now, a lot of the microcontrollers these days are what they call 5 volt tolerant. So you can imagine they'll tolerate you, but they're not super pleased with it, right? And you never want to be 5 volt tolerant. You want to be 3.3 and happy, right? So some of them aren't, right? Some of them may not be 5 volt tolerant, and 5 volts on your pin will just blow it up. For example, way back in the days of the go-kart for Team Phantom, we were working on the kart super late one night over winter break, and we accidentally put a voltage higher than 3.3, right? Anyone want to guess which voltage? You guessed it, 24 volts. This definitely killed the microcontroller. Boom. That was a fun night. And after we put that, even for a second, right, that 24 volts is higher than the logic level of the microcontroller, definitely higher than this 5 volt tolerance level. And so we fried the sucker, and it was dead.
Just why?
Say again?
Why?
It was an accident, I swear. We had, because like the foot pedal of the car, so like where you put your foot, the sensor we were using didn't have very good resolution, so when we just use it as 5 volts, you could barely read a voltage difference as the person stepped on the pedal. So we put 24 volts on here so we could read a sliver of that 24 volts from like 0 to 3 or something. But then wires came loose, and then the 24 volts made its way around and hit our guy, and then we died. And then anytime we'd turn the thing on, you could feel it just burning and bubbling, and it was really hot. So never do that. Always be careful to what your logic level is and what voltage you're using, and make sure you stay within that as much as possible. This is important also, not just for our simple 0 or 1 GPIO, but for any other communication protocols that you use when you're talking to a sensor. If it's talking on a different logic level than you, then you're going to have a tough time understanding each other, right? It's like different languages almost. You need to make sure they're matched up to be able to chat. So with the GPIO, like I mentioned, you can go in or out, so inputs or outputs. So
I have a question.
yeah.
What can you do to match them up if they're not matched up?
Good question. So let's say my guy, I have a Uno. So I have an Arduino Uno, that's 5 volts. That's its logic level. And then I have a Team Phantom guy. Phantom. That's 3.3 volt logic level. And they don't get along, right? So what some smarter people than us have invented is what you would expect, right? If you're speaking Spanish and someone else is speaking Japanese, you get a translator. So there you go. And translators are very special people because it takes a lot of work to listen to two people talking and translate between them. So the translator will be able to take in this 5 volt logic level and spit out the right 3.3 volt one for Phantom, or for the TMS570, or whichever 3.3 volt logic level you're using, and vice versa. So it can go one way and it can go the other way. And this translator, usually it's called a logic level converter. Logic level. And what's important to know when you're picking these is usually the speed. So you can imagine if the Uno turns on 5 volts just once and leaves 5 volts on, a logic 1 forever, it's pretty easy to convert that into a turn on 3.3. But if I'm turning on 5 volts and turning it off and turning it on and turning it off really quickly, sometimes it's hard to keep up. So you have to be very careful about what speed this thing is rated for. If it's not rated for the speed you want to send zeros and ones at, you're going to have a tough time because it's going to lag and it's going to miss a lot of your transitions, and it may just miss some of the bits that you're trying to send, some of the ones and zeros. Right? So you have to be very careful. A lot of the time, these are specified for specific communication protocols, so things like I2C and SPI and UART, which we'll talk about another day. And so they should have the same speed capabilities, but you always want to make sure. If you really want to, you can create your own logic level converter out of some transistors, but that's just for fun, and Jared can talk about that another day. So GPIO, we're chatting about this. So the first thing you can do, like we said, is so let's say you're using it as an input, right? We want to read from the world around us. So if I use a GPIO as an input, I can read if there is a logic 1 or a logic 0 on that pin that I'm using, right? So a microcontroller is this little square, right? And that square has a bunch of silicon and dies and chips inside it, and all these things, we don't know how they work. Now it has these little metal legs on the outside. And these metal legs are often called leads. Leads is popular. Oof. Leads, sometimes pins. Pins is very popular. And they're the way that the silicon inside here, all this stuff that's in here, interacts with the physical world around it, right? So these metal leads will connect to little exposed pieces of metal on a circuit board. You'll solder it onto these, and then you'll have little wires within a circuit board. And they're often called traces, but they're essentially just little tiny strips of copper wire that go along your circuit board and talk to other things, right? So maybe like another microcontroller is here and we can chat, or there's a sensor that goes somewhere else and we can chat there as well. We can read from a lot of different places. Okay. So, and it's interesting because we may have a fixed number of pins on the microcontroller. Say in this case we have 16 pins, right? All right, back to this, eh? So let's say we have 16 pins. I think that's the smallest I've ever typed in my life. So let's say this guy has 16 pins. The microcontroller probably has a lot more peripherals and capability than just 16 different things it can do. And so what often happens is this thing called multiplexing, right? So multiplexing is a way to connect one of these tiny little pins to multiple different building block modules within our microcontroller. So it may be a module to do our GPIO input. There may also be a module that does analog for us, or a module that does some sort of specific communication for us. That may also come out on this pin that we want to use. And so the first thing you usually have to do is connect your pin internally to whatever building block you want to do. And that's called configuring your pin. On the TMS 570, which is the microcontroller used by Team Phantom, we have a thing called the pin mux. So multiplex is also shortened as mux. So this pin mux will allow you to select exactly what function you want on that pin, right? So once you know that, let's say I want my pin here, I have to configure it as a GPIO, right? I want to do digital stuff. I want to do it now, and I want to do, I want to read from the world. I want it to be an input. So you say, I want to be GPIO. I also want to be an input. You have to tell it, because it doesn't know if you want to read stuff or send it out. So I want to be an input. Thank you very much. These are probably the two biggest things you need to do once configuring a pin for the first time. And with an input, you have a lot of different options in terms of how you want to configure that pin. So one of the biggest things you can do on an input is enable or disable the pull-up and pull-down resistor. So if this is my microcontroller, so it's a big square, right? Just want to zoom into my one pin. So my pin's here. Let's move it over a little bit. Pin's here, right? So this is where I would interact with the rest of the world, right? This pin would be soldered on a circuit board and it'd go other places. It'd live its best life talking to whoever it wants to talk to, reading in signals, sorry, the other way, talking with whoever it wants to talk to, reading 3v3s or reading zeros. But sometimes nothing comes up, right? Let's say it's reached a lonely spell, there's no one out there for our pin. And so we don't have a 0, we don't have a 3.3, there's no one talking to it. This pin is what it ends up in what's known as a floating state. This is often what happens when you don't have anyone to talk to. You're kind of floating, lonely, you're not sure if you should be a 2.3, you're not sure if you should be a 0, which I'm sure you guys have felt before. You're kind of in nowhere, in nowhere land. So what the pull-up and pull-down resistor allow you to do is to get rid of that undefined state. This floating state is confusing because we don't know we're reading in signals, right? Whereas an input, we don't know if 3.3 volts is on here, if 0 is on here. And what actually happens usually is that this pin will float to sort of an undetermined voltage based on the amount of noise around it, based on the magnetic fields around it, everything that's going on. It may float to some kind of soft 1.4 volts, 1.2 volts, something kind of not in between. And so if you get unlucky, it could float to show you an accidental 1 or an accidental 0. So you really want to remove that undefined kind of confusing floating state. We don't know what that means. We don't know what actually may happen. So the pull-up and the pull-down resistor are a fantastic tool because they allow you to define your states properly. And so let's say I enable a pull-up, right? I'm pumped. Hit enable my pull-up. What that means is that internal to the microcontroller, this is not external, this is inside the chip, I can enable a resistor, which is really cool. I can turn on a resistor, which is kind of weird when you think about it, but that's what's actually happening. There's a little switch that connects this resistor path to my pin. Now, usually it's a really high resistance. 30 to 40K is pretty common for internal pull-ups and pull-downs. So the higher resistance, the weaker your pull strength. So I don't have as much strength on the line as I would if I had 1 ohm. If I had a 1 ohm resistance, I'd be really strong in my pull-up capability. And what that means is that when my pin is floating, when it's confused and not in a really defined state at 3v3 or 0, the pull-up will save me because even though this pin's floating, the pull-up is going to bring it up to 3.3 volts. It's going to put me into a defined state. So I'll know I'm at 3.3. And what's nice is that even when my pin is being driven by an actual signal from the outside, if it's an actual 3.3, my microcontroller doesn't matter, doesn't care. The 3.3 and the 3.3 here don't fight. But if it's a 0 that's coming up, if I'm actually reading a 0, this resistance is so weak that it's not going to interfere with the external signal. If I had a 1 ohm resistor here, then it's a very weak resistance and a lot of current would flow here. And my pin would take on that 3.3 volt value. But because it's such a high resistance, it doesn't bother anybody. It gets out of the way. The 0 volts can go through and we can read 0 volts fine. Now this is also true the opposite way. Let's say when I'm floating, I don't want to be 3.3. When I'm floating, I want to be 0 volts, right? Well, I can just enable the pull down. Right, something like 40 kilo ohms. I can enable the pull down. And so whenever I'm at a floating state, my pin is going to read 0 volts. And so that way I'll never get an accidental floating high or floating low. I'll always know exactly what my pin should be. So we don't get any mistakes or any misrepresented signals. I think we'll leave it off for there today. Any questions on these concepts?
can we use multiplexing and logic converter at the same time?
Say again?
Like, no, I think I just answered the question myself. Never mind.
You said, can you do multiplexing and logic level conversion at the same time? Is that what I heard?
Yeah. But I think it's not possible, right? It doesn't make sense.
Yeah, usually, that's a good question. Usually you set up your multiplexing once, right? So you set this up to happen once at the very start so you can configure exactly what all your pins are going to do. And then you're not changing that usually mid-operation. So you do that once, and then the logic level converter happens outside of your microcontroller, right? So these two are the microcontrollers. This is some third-party external chip that's doing my translation. And so this can do whatever it wants whenever, but that multiplexing happens usually just once in this scenario, right, where you're setting up a pin for the first time. Does it make sense?
Yeah.
Okay. More questions? I need at least 3 before I can leave.
What are you gonna cover next week?
Okay, not a question. Damn it, John.
Is embedded hard to learn?
Okay, that's a good question. Yeah, next week, John, we'll do the output side of GPIOs, so output, and then we may get into some of the analog stuff, so analog to digital conversion and digital to analog. Embedded it's not hard to learn. It's pretty interesting to learn, actually. It depends on who you're surrounded with and how many resources you have available to you. Google is obviously a great resource, but since we're in such a great community of learners and teachers, for us it should be really easy. So whenever you have a question, just send a message in Slack, and we'll be there to answer it. But I'd say the only hard part is whenever you get a problem that you don't know the source of, which is something we're going to talk about in a specific lesson, how to debug those hardware problems. Because if you come from an electrical background, you're going to really understand how your circuit board is working, if you have any problems on it, how that might show up in the microcontroller. But then you're going to be weaker, obviously, on the coding side. If you come from a coding background, you're going to crush the coding, so it'll be so easy. But then your line of code, which is supposed to work, just doesn't do what you want it to do, right? And so that's probably the hardest part, where you need to figure out how you solve a problem that may not be your code. It may be some problem external to what you're writing in the hardware, and debug in that way. But we'll chat about that and different strategies to go about that in a different lesson for sure. Thanks for bringing that up. Okay, last question. Unless you have more.
This is a question for everyone else, actually. It's more about if everyone could give their feedback on the pace and the content of the lesson so that Dave knows what everybody's level is at. Because I know over here we have some people perhaps who've never done embedded before, and maybe there's others that have a lot of knowledge. So you can always communicate that to Gabe so he can tell you in advance what type of lesson it's going to be.
Yeah, thanks. If you guys want to, feel free to say out loud right now. If you don't want to, you can just message me or put in the chat. If it was too fast, too slow, or just right, let me know.
I thought it was really good.
Okay. Anything else?
You taught, I understand more than my whole 352 class, so.
Great. It's okay. I didn't understand anything from there either.
I'm just taking a wild shot in the dark. Did you work at Tesla before?
No, I worked at Intel.
Oh, I see. Okay. Makes
Yeah.
sense.
You're getting some feedback in the chat box.
Okay, cool. Yeah, it was cool because when this rocket launch happened, they actually launched a Tesla Roadster into space. We still don't know why, but Elon wanted to. And because they were launching that Roadster, like all of the Tesla employees were like super pumped about it too. And so like the same way you see like all those engineers show up in like the control room when the rocket's launching and all super pumped, like that same thing happened at Tesla, and it was like a super crazy feeling of like seeing like an engineering marvel happen before your eyes. It was crazy because they landed these two rockets at the same time, like within seconds of each other, which has never been done before. And even though I was an intern and had literally nothing to do with any of these things remotely, not even close, it was still cool. So yeah, it's great to see like how far engineering has come and how far you guys are going to take it into the future. So I'm excited for that. Great. Thanks, guys. We'll leave it off there and enjoy your evening. Feel free to send any more messages in the chat or message me directly on Slack or anywhere else, and I'll be happy to get some feedback.
Should we have a quick embedded meeting?
Let's do it.
Just to kind of update everything. Yeah, anyone who's not in embedded, feel free to head out.